If my memory serves me, in the last lecture, we discussed a marvelous theorem about Riemann integration. To be precise, the theorem provided you a necessary and sufficient condition for a bounded function to be Riemann integrable. The statement is as follows. And the theorem is popularly called Riemann-Lebesgue theorem. And it is a place where two theories meet, Riemann integration theory and Lebesgue's measure theory. Let f be a function from closed bounded interval AB to R, be a bounded function, then f is Riemann integrable if and only if set of points at which f is discontinuous. Has Lebesgue outer measure 0. In other words, the function is continuous almost everywhere. Further, in case it is Riemann integrable, the function will be measurable. So you can start thinking about Lebesgue integration, and the Lebesgue integral will coincide with Riemann integral. In this case, f is measurable and Lebesgue integral of f recaptures Riemann integral. Okay, so this is a beautiful theorem, I would consider, that we have proved, of course, with some details that I have not supplied, but given as an exercise, but that I hope you can do it yourself. Okay, but the content of the theorem is very important. And there is an intuitive way to understand this statement, or an intuitive way in which this theorem can be viewed, or at least how I would like to see this theorem is as follows. Suppose f were integrable, then you know that you can decompose the integral into two parts. So what I am going to do is I split the integral over AB, Lebesgue or Riemann, into two parts. Let us say integral over df plus integral over complement of d in AB f, where d is set of points where f is discontinuous. set of all x in AB where f is discontinuous. In fact, D need not be an interval, but it is sitting inside AB. With a little bit of cheating, let me tell you that f is continuous on the complement of D. And you know that continuous functions are integrable. Therefore, integrability of f on AB is decided by integrability of f on D. If measure of D is 0, then the integral of f over D would be 0. That we have seen. Okay. Therefore, what Riemann-Lebesgue theorem says is that a function is integrable, or an integrable function is one for which the points where the function is discontinuous contributes nothing to the integral. Remember, if the measure of D is 0, the first term contributes nothing to the integral of f over AB. Therefore, if you look at Riemann-Lebesgue statement, it says that the integrable functions are those for which are you able to hear me properly?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, thank you. So the Riemann-Lebesgue theorem says that the integrable functions are one for which the integral over set of discontinuities contributes nothing. Okay, is that okay?
Yes.
The points where it is not continuous contributes nothing to the integration value of the integral. So that's what the Riemann-Lebesgue lemma says in intuitively. Of course, there are some issues like how do you say that integral over complement of D over a continuous function will be integrable and so on. Because Riemann integration is only on an interval, but AB minus D is not an interval in general. Okay, but this is roughly the way in which I would like to see it. Okay, maybe I can even write in record. Thus, Riemann-Lebesgue theorem states that, or says that, an integrable function is one for which the points where that function is discontinuous contribute nothing to the value of the integral. Okay. Next, before going to the main project, I would like to make a few comments. One is regarding one of the convergence theorem that we proved, namely bounded convergence theorem. We have derived bounded convergence theorem as a special case of dominated convergence theorem. Yes or no?
Yes, sir.
And perhaps while you studied Riemann integration theory in your bachelor's, possibly, you might have seen an analogous of bounded convergence theorem in the Riemann setting. Perhaps I might have stated it while I reviewed Riemann integration theory. Okay, so let me state the theorem first. Okay, so what I want to say is that the bounded convergence theorem is stated even in the setting of Riemann integration theory, and the statement is as follows. And usually it is called Arcela's bounded convergence theorem. The Arcela bounded convergence theorem. The statement goes as follows. Let Fn be a sequence of functions which are Riemann integrable on AB. Suppose that these functions converge pointwise. Suppose that sequence Fn converges pointwise to a function f. Bear in mind that it is not necessary that f is Riemann integrable. Even with Riemann integrability of each Fn, we cannot assert Riemann integrability of the limit function. Okay. And further, suppose that each of these functions is bounded. Suppose that modulus of Fn of x is less than or equal to k for all n in n for with a single constant and for all x in AB. Then the sequence of integrals, integral a to b Fn of x dx converges. And in case the limit function f is Riemann integrable, that is not certain. And in the event that f is Riemann integrable, on AB, we have integral of the limit function Riemann integral is equal to limit of the integral. Look at the statement. It is analogous result that you have proved with the name bounded convergence theorem in the setting of Riemann integration. Do you agree? Each function is Riemann integrable, functions converges pointwise, and the sequence is uniformly bounded by a constant k, then integral of Fn converges. Where it converges, that we have to be careful, because we don't know small f is Riemann integrable. We cannot assert in general, but if f is Riemann integrable, integral f is equal to limit n tending to infinity integral f. Do you see this theorem as a special case of bounded convergence theorem that we proved? Yes or no? Are you able to hear me?
Yes, sir.
Question is, can you see this theorem as a special case of bounded convergence theorem? We proved. What was the statement there? Suppose each Fn is Lebesgue integrable. Here you have Riemann integrable. Just now you proved, or you restated, that Riemann integrability implies Lebesgue integrability. So you have a sequence of Lebesgue integrable function, and you have modulus of Fnx less than or equal to k, and that will tell you that each Fn is Lebesgue integrable and integral Fn is convergent. So first part is over. The sequence integral Fn converges. That is immediate. Now, in case f is Riemann integrable, the Riemann integral will coincide with Lebesgue integral, and you know from the bounded convergence theorem that integral f is equal to limit Fn. Yes or no?
Yes, sir.
So now is it clear that this is only a special case of, just use the fact that Riemann integrability will imply Lebesgue integrability, and moreover Riemann integral and Lebesgue integral will coincide. Using that fact, you can see that this is a special case of bounded convergence theorem. Proof. I will just write special case of Lebesgue monotone convergence theorem. We already proved. As I told you, the statement as such might have introduced in your Riemann integration course, but usually, including most of the standard books, leave the proof saying that the proof is not elementary. But now we have a, I will not call elementary, but an easy proof via Lebesgue measure and Lebesgue integration. Okay. So at the introductory real analysis course, when this Riemann integration is being introduced, this statement might have made, but they don't attempt to prove it. And most of the standard books like real analysis by Bartley and Sherbert, etc., if you see, they just comment that the proof is beyond the scope of this book, or the proof needs advanced tools and so on. But right now, with the help of Lebesgue integration, Lebesgue measure theory, etc., we have seen that this statement could easily be deduced as a special case of Lebesgue bounded convergence theorem. So that's the remark that I want to make. Further, since the statement involves only Riemann integration theory, it is natural to expect a proof based only on Riemann integration. Yes or no?
Yes, sir.
Yes.
Yes, sir.
Though we have proved it using Lebesgue idea, etc., I'm not saying that this theorem doesn't have a proof independent of Lebesgue integration. In fact, it can be proved just by using ideas that you studied in calculus. But possibly the proof may be lengthy and so on. But those who are interested, recently I have seen a nice article which states this theorem and provides a proof in the elementary level without using Lebesgue integration and so on. Okay, so I will just quote that reference here. Those who are interested can read it. Okay, for an elementary proof, when I say elementary here, I mean proof which doesn't involve measure theory, etc., and which can be understood with your real analysis background. For an elementary proof of Arcila bounded convergence theorem, refer the following. Okay. In fact, the title of this article itself is a truly elementary approach to the bounded convergence theorem. The author's name is Jonathan Levin. And this article appeared in American Mathematical Monthly. Where several articles of such kind aimed to broad audience appears. And it is published in 1986, not that old. And it has only 2 pages, a short article, 395 to 397. I should say, as in fact, I could have told it in the beginning of this course itself, but let me at least tell now. Better late than never. Yes. So those who like to pursue mathematics further should read beyond standard textbooks. Articles you have to read, and the best starting points are articles like this, which doesn't need much background, which doesn't need research level knowledge. And some good venues to start with are, maybe I have told before also, American Mathematical Monthly, where several such articles of simple proofs of things that you have already studied as part of your several course, etc., appears. Okay, so that will give you a confidence how to read articles and how to think of different proofs other than which is available in your course and standard books and so on. Okay, American Mathematical Monthly is one such publication, and there are many. There are a few Indian publication also. Resonance, I don't know whether you have heard about Resonance. There also many such articles appears. Then mathematics newsletters, okay. All these things are good venue. Anyway, you have to do a project maybe in the next semester. So you have to read something beyond standard textbook. And I would recommend to start with reading something beyond the textbook. These are the best places to look. And slowly then you can go to research level articles. Okay, to start with these type of articles which doesn't need much background, and at the same time which you cannot see in any standard textbook is good enough. Okay, anyway, so I just wanted to introduce the bounded convergence theorem in the Riemann setting and say that it is a special case of Lebesgue bounded convergence theorem. So a general theory gives you an easier proof for a particular case. And this is not something new in mathematics. Okay. Sometime when you do a more general theory, that will give you an easier approach in the already known setting. Okay. Now, I think I should give you some examples where to use this convergence theorem, how to use this convergence theorem, etc. So let me give you a quick example. So I want to compute integral of f dm. Dm should suggest you that I mean to have the Lebesgue integral, where f of x is defined as follows. One by root x, let us say x in 0, 1 and 0 when x, or maybe, yeah, x is equal to 0. Even if I take 1 by root x for the closed interval 0, 1, I don't mind. Because for a Lebesgue integral to deal with, you don't want boundedness. Okay. Anyway, so I have defined fx like this. At first, you should observe that you cannot handle this with Riemann integration as such, because the function 1 by root x is not bounded on the interval close to 0, 1. Do you agree?
Yes.
Note that the function is unbounded on 0, 1, and hence, as such, we cannot apply theory of Riemann integration. Do you see that the function is continuous almost everywhere on closed interval 0, 1? Where the function is not continuous is at 0, right? Yes or
Yes.
no?
Yes, sir.
Yes, sir.
Therefore, this function is continuous almost everywhere and hence it is measurable. Okay. Note that f is measurable. So measurability is one starting point where you can deal with the Lebesgue integration. Without this, you cannot talk about Lebesgue integration. So it is measurable. Okay. Now what I do is I will consider a sequence of functions converging to fx, and then deal the integral of f via integral of fn using some convergence theorem. That's the idea. So to get the sequence of function converging to f, I will cut the interval into, let us say, 2 p's. 0, 1 is the interval. Let me cut it into 2 p's by introducing 1 by n. Okay. And let us define fn of x is equal to 1 by root x for x in 1 by n 1 and 0 otherwise. Do you see that fn's are increasing? Try to compare fn and fn plus 1.
Yes, sir.
Fn is, it is not hard to see. So let me just write that fn is increasing. Sequence fn is increasing. Now, can you guess where this converges to as n tending to infinity? Where fn converges to?
F.
Yeah.
F.
Further, fn converges to f. Okay. So this is a perfect situation to use.
Monotone convergence theorem.
Monotone convergence theorem. By MCT, integral 01 Fn dm converges to integral 01 integral over 01 f dm. Okay. Now, what is integral of Fn over the interval 01? Okay. Now, integral of Fn, Lebesgue integral over the interval 01 dm. Look at Fn. Fn is 0 outside 1 by n1. Okay. Therefore, this finally coincides with integral over 1 by n1 Fn. And what is Fn? 1 by root x dx. And 1 by root x is continuous on the interval 1 by n1. Do you agree?
Yes, sir.
Yes.
And therefore, you can talk about Riemann integration. Maybe I will write one more step. This is equal to integral 1 by n1 Lebesgue integration, Fn dm. But Fn's are continuous in 1 by n1. Therefore, it is Riemann integrable. Once it is Riemann integrable, the Lebesgue integral will coincide with the Riemann integral. So it is 1 by n1 usual Lebesgue integral Fnx dx. That is 1 by n1 Fnx is 1 by root x dx. And that you can perform. Root x is x power minus half. So x power half by half between the limit 1 by n1 and so on. So you will get 2 times 1 minus 1 by root n, I hope. So this is integral of Fn. Therefore, as n tending to infinity, therefore, integral of f dm, Lebesgue integral, is equal to limit n tending to infinity 2 times 1 minus 1 by root n. And that you know it is equal to 2. So we have computed the Lebesgue integral of f dm. Okay. In fact, you know integral 0 to 1 by root x. How do you calculate it? In Riemann integration itself, you will calculate it under the name improper integral. Note that integral 0 to 1 by root x dx. The issue is at x is equal to 0. Therefore, it is an improper integral of the second kind. First kind is what in which the intervals are of infinite length. Here, interval is of finite length. But the issue is with the integrand. Integrand becomes unbounded at one point, namely 0. So what you will do is you will avoid it and you will take epsilon to 1 by root x dx, and then make epsilon tending to 0. Do you recall?
Yes, sir.
This
Yes,
is called
sir.
Yes, sir.
improper integral. Okay, improper integral. So it is not actually Riemann integral, but it can be handled with Riemann integral using the improper integral technique. Okay. Now you do this, you will get 2. Okay. You find this limit epsilon tending to 0 plus and so on, you will get 2. Okay. I just wanted to give you an idea of how this convergence theorem can be used, and at the same time, how this interconnection between Riemann integration, Lebesgue integration, etc. can be explored with a simple example. And that was my intention. Okay. So again, before going to our next main project, let me give one more comment, or rather a passing remark. If you recall our progress in Lebesgue integration, especially the definition of Lebesgue integral, it went as follows. First, you defined Lebesgue integral for a non-negative simple function. Okay. Lebesgue integral for a non-negative simple function. As a next step in the hierarchy of that definition, we define Lebesgue integral for a non-negative extended real valued measurable function. Measurable function. And then you have defined integrability. First you define integral and then you have defined integrability. How did you define integrability? If the integral happens to be finite, we say that the function is integrable. Yes or no?
Yes, sir.
Now, as the last step, you went to any function, need not be non-negative. Okay. There, first you define integrability. How did you define integrability? Using positive part and negative part. You can write f is equal to f plus minus f minus. If integral f plus dm, comma, integral f minus dm, both are finite, then you say f is integrable. And once it is integrable, you define integral f dm as integral f plus dm minus integral f minus dm. This is how we developed Lebesgue integration for a general measurable function, real valued measurable function. Also, I want to stress the fact that the integrability comes after defining integral for a non-negative function. Whereas while coming to general function, first you define integrability, then comes the integral. Are you with me?
Yes, sir.
That order is important. For a non-negative function, first you define integral. Integral can be finite or infinity. If it is finite, you declare it to be integrable. Now, while coming to a general function, first you check integrability. And once it is integrable, you define integral. Okay. Now, anyway, so if you see the progress, you stopped with Lebesgue integral of real valued function. Now, next question is, why not complex valued function? Okay, so that's what I wanted to hint at. It's not hard to develop. It's very easy to develop the idea of Lebesgue integral of a complex valued function. Okay. Next, let us see Lebesgue integral of a complex valued function defined on some subset E of R. Complex valued function f from E subset of R to C, where E subset of R is measurable. As you know, for Lebesgue integration, first you need a measurable function. So I have to deal with measurability of a complex valued function. Okay, that's not hard. First thing, in fact, the crux of the matter for the entire integration theory for complex is that a complex valued function can be written as follows. Okay. every complex valued function f can be written in the form f is equal to real part of f of x is equal to real part of x plus I times imaginary part of f, where real part of f and imaginary part of f are real valued, as you all know. Now, for measurability of a complex valued function, we declare that a complex valued function f from E subset of R to C is measurable if, natural definition, right? Both real part and imaginary part are measurable. If both real part of f and imaginary part of f, which are real valued, are measurable. For instance, the theorems that you have proved in about measurability of a real valued function can be extended in this case also. You have proved that continuous functions are measurable. Here also you can prove continuous complex valued functions are measurable. You have seen that if f is measurable and f is equal to g almost everywhere, then g will be measurable in the case of real valued function. That can be extended. Okay. So I am not writing all those things. So most of the theorems that you have studied about measurability and measurable functions, real value, can be extended to complex value. Now, let us take a function f which is measurable from E subset of R to C. Be a measurable function, complex valued, measurable function defined on a measurable set E. Defined on a measurable set E. I am attempting to define Lebesgue integral of f. Okay. Write f equal to real part of f plus I times imaginary part of f. If now real part of f and imaginary part of f are real valued, and you know what is the meaning of integrability of real valued function. If integral over E real part of f dm and integral over E imaginary part of f dm both exist and finite, meaning they are integrable, then Lebesgue integral over E f dm I define as integral over E real part of f dm. As I told, this is very well anticipated. Integral over E imaginary part of f d. This is how we define integral of a complex valued function, provided both real part and imaginary part are integrable. Okay. Now, please remember that for a real valued function, integrability boils down to whether f plus and f minus are integrable. Also, bear in mind that a real valued function f is integrable if and only if integral of mod f is less than plus infinity. Can you recall?
Yes, sir.
So integrability
Yes,
of f and integrability of mod f are same. Okay. Because if integral mod f is less than plus infinity, integral of f plus and integral of f minus will be finite, and therefore you can define integral of f df. Similarly, let f be a function from E subset of R to C, be a measurable function on a measurable set E, then integral over E f dm exists. That is integrable if and only if integral over E mod f dm is finite. How does it follow? Because modulus of real part of f is less than or equal to mod f, and modulus of imaginary part of f is also less than or equal to mod f. Now you use integrability for a real valued function. Okay. Further, integral of f dm has absolute value less than or equal to integral of mod f dm. Okay. In that case means in the integrable case. Now, like the convergence theorem, wherever you can extend it to the complex valued, you can extend it. For instance, you cannot talk about monotone convergence theorem in complex case. There is no monotonicity. Fnx less than or equal to fn plus 1x. You cannot define less than or equal to relation in complex. Okay. Therefore, whichever results that you can extend to complex is valid in complex as well. Just for an instant, let me tell you that the dominated convergence theorem you have proved in the case of real valued functions very well go for complex valued function also. Okay, let me just state it. Dominated convergence theorem for a complex valued functions. Let fn n element of n be a sequence of complex valued measurable functions defined on a measurable set E subset of R if what are the two conditions for DCT? One is that the sequence of functions converges almost everywhere. F of x is equal to limit n tending to infinity fn of x almost everywhere on E. And second condition is that all the functions in that sequence is dominated by a single integrable function. There exists a single integrable function G such that modulus of fnx, it's a real number, less than or equal to g of x. Obviously, g should be real valued. Otherwise, you cannot talk about inequality like this. If g of x is complex, almost everywhere, then the theorem says that each fn, comma f are integrable. And it says that integral over E mod fn minus f dm tends to 0 as n tending to infinity. I have put this as a remark, and in particular you will get that integral over E fn dm converges to integral over E f dm. In particular, integral over E fn dm converges to integral over E f dm. While I proved DCT for a real valued function, I wrote the statement as integral E fn dm converges to integral E f dm, and I put a remark that in fact, we can prove integral over E mod Fn minus F dm tends to 0. So now I clubbed the remark and the statement that I have given there as n tending to infinity. So this is DCT for a complex valued measurable functions. Okay. So I will not discuss in detail about the complex value because it's just matter of fact that a complex value can be split into real part and imaginary part, and then you apply the theorems and results for the two parts separately. So we will not deal with the complex valued. However, I just wanted to mention that you can extend Lebesgue integration even for a complex valued function. Okay. So this finishes whatever small comments that I want to make. And with this, I will stop here and then I will go to the next main agenda or next our main project. The project or the goal is as follows. If you remember, after Riemann integration theory is introduced, what did you explore there? And how do you perform Riemann integration? Okay, as definition etc. says is well and good, but how usually one computes Riemann integration? Are you using partition etc. etc.? In practice, how do you compute an integral, Riemann integral? Yes. Are you people there? Can you hear me? Is the question clear? You know that Riemann integration is defined via upper sum, lower sum, partition, etc. etc. But suppose I am giving you a definite integral, let us say integral a to b fx dx. How do you in practice compute it? Say integral 2 to 3 x cube dx. How do you compute it? No, you don't know or you don't want to answer. Let me tell you that it is really embarrassing because first of all, in an online mode, I don't know whether it is because of audibility issue you are not responding. This question is definitely not complicated. Even a first year BTech student can tell me integral 1 to 2, let us say x cube dx. How do you compute?
So take a function gx such that that's differentiation is x cube by x cube.
So you
And
will
then,
find the antiderivative, right?
yes,
And then
yes,
you
sir.
will perform it. Okay. What facilitate you to do this? How do you know that integral, which is defined via upper sum, lower sum, etc., is same as calculating the antiderivative and then evaluating at the two endpoints and subtracting? How do you know it? In other words, how do you know that there is some connection between integration and differentiation? Who told you?
Fundamental theorem.
The fundamental theorem of calculus. This is what I wanted from you. So after Riemann integration, next thing usually anybody does in that course is to explore the relationship between Riemann integration and differentiation, and that relationship is revealed via the so-called fundamental theorem of calculus. And our next aim is to see fundamental theorem of calculus in the which setting? Lebesgue integration technique or Lebesgue integration theory. What is the analog of fundamental theorem of calculus? It's not as easy as you think. That's our next main target. It may run to this lecture plus next lecture. Okay. Of course, with avoiding some details. So I have already told you what's our next aim, to explore fundamental theorem of calculus in the Lebesgue integration technique, or to explore is there some connection between integration in the Lebesgue sense and differentiation. Okay. I think the best way to start with is to recall what is fundamental theorem of calculus in the Riemann setting first. Okay. So I will do that first. Basically, the fundamental theorem of calculus, as I told you, gives you the connection between the notions of differentiation and integration. Okay. And if you see, usually the fundamental theorem of calculus is stated in two forms, or the theorem has two parts. One says that integral of derivative. One says about integral of derivative, and the second part talks about derivative of the integral. Okay, so usually called fundamental theorem of calculus version 1 and fundamental theorem of calculus version 2. Okay, so let me restate it for you. Okay. As I told you, roughly speaking, both the part clubbed together gives you that integration and differentiation are inverse process. But I should say that there are some subtleties, and those subtleties you cannot overlook. You cannot just think that differentiation and integrations are inverse process. Yes, roughly it is true, but to the core, it is not the correct way to say what is fundamental theorem of calculus. There are some subtleties. You cannot just say that if you differentiate and then you integrate, you will get back the function. That is not true in general. Okay. So with that note, let me state the fundamental theorem of calculus that you might have learned in Riemann integration theory, FTC first version. Okay. FTC first version. That is how I would like to call what the first version says. Let f from AB to R, small f from AB to R, and let capital F is a function from AB to R. Both are functions. And let us assume the following things. Capital F is continuous on AB. And 2, capital F is differentiable and capital F dash of x. This is what you are saying. You will find a function whose derivative is the given integrand fx. You may ask, once f is differentiable, then obviously it is continuous. Then why you are putting the first condition? The answer is that f is differentiable. I am not assuming at all point, okay, except at a finite number of points. On AB. So I don't want differentiability on the entire AB. I don't want the derivative of capital F to coincide with small f on the entire AB. Okay. I want it except at finite number of points. And suppose also that small f is Riemann integrable. So the given function small f is Riemann integrable, and you can find a function capital Fx whose derivative is small f except at some finite number of points. Then the fundamental theorem of calculus first version tells you that integral a to b small f of x dx, Riemann integration, is equal to capital FB minus capital FA. Or integral a to b, what is f of x? It is capital F dash x. Dx is equal to capital FB minus capital F. So this is talking about integral of the derivative. Okay. But let me also make a note here that you should be careful. It is not true in general that you might have observed this while discussed about the fundamental theorem of calculus. It is not true in general that integral of a derivative, integral g dash x dx is equal to gb minus ga. This is not correct always. Though you may feel like I have written integral a to b capital F dash is equal to capital FB minus capital FA, that requires certain condition on small f, certain condition on capital F, and so on. Okay, that is not true in general. So that's why don't think in this manner. Integral of g dash is always equal to gb minus ga. That is not correct. Okay, you can easily find functions g which is differentiable, but integral a to b g dash is not equal to gb minus ga. Okay. And the second version of second form of fundamental theorem is as follows: FTC second version. Basically, the first version told you about integral of the derivative. Now you will have derivative of the integral. Let f be a function from AB to R, Riemann integrable. Please bear in mind that Riemann integrability doesn't require the function to be continuous. Therefore, this f may not be continuous everywhere on AB. Suppose f is continuous at some point. Suppose small f is continuous at a point C in AB. Now, since it is Riemann integrable on AB, I can talk about integral a to x f of t dt for any x in AB, and that I will call as capital Fx. This is usually called indefinite integral for every a less than or equal to x less than or equal to b. Capital F is well defined because small f is Riemann integrable. Okay. Further, if small f is continuous at C, this capital F would be differentiable at C. Then the indefinite integral capital F is differentiable at C. If the integrand is not just Riemann integrable, but in fact it is continuous at a point, then the integral function will be differentiable at C. And further, capital F dash C is equal to small fc. This is for a point where small f is continuous. Suppose f happens to be continuous everywhere. In particular, if small f from AB to R is not Riemann integrable alone, but it is in fact continuous, then the indefinite integral capital F is differentiable and capital F dash of x will coincide with small f of x for every x in AB. Look at capital F. It was integral of small f. So this tells you that if you integrate and then differentiate, you will get back the function. First version was talking about the other way around. Okay, differentiate and then integrate. This is integrate and then differentiate. So basically, clubbed together, both the versions tells you that integration and differentiations are inverse processes. Again, I highlight the fact that there are some subtleties. It's not just that they are inverse processes. There are some subtleties. You should not overlook those subtleties. So you please keep the precise statement in mind. FTC first version and second version. As I told you, our aim is to analyze these type of theorems in the Lebesgue setting, Lebesgue integration technique. We shall analyze FTC in the Lebesgue integration setting. For that, I have to collect so much of prerequisite materials, background materials. So we shall do that one by one. And finally, maybe by next lecture, I shall be able to state and prove what is fundamental theorem of calculus for a Lebesgue integral function. Okay. So I shall start by introducing certain class of functions that all needed as a background work for this main target. Okay. So far, so good.
Yes, sir.
Yes,
So
sir.
at least what we want to do next is clear, right?
Yes, sir.
Yes, sir.
Yeah. Now let us try to do that by collecting the background material. Okay. Let us start by fixing some notation. Fix an element. Maybe before that, I will introduce one more notation. Otherwise, every time I have to write, let f be an Lebesgue integrable function on AB. Instead of that, if I introduce the following notation, it will be convenient. Introduce the notation capital L1 AB is equal to collection of all functions f from AB to R or AB to complex also is okay, AB to K, such that f is measurable because measurability is a minimum condition required for integrability, and integral AB f dm is less than mod f dm, sorry, is less than infinity. Basically, you are collecting all those functions which are Lebesgue integrable. Do you agree?
Yes, sir.
Whether it is real valued or complex valued, the Lebesgue integrability reduces to integral over AB mod f dm is finite. So you are collecting all those functions which are Lebesgue integrable. Capital L for Lebesgue. 1 stands for what you will come to know in the next few lecture. Because if you see, I have integrated only mod f, not the powers of mod f. Okay, if you integrate mod f power something, then you will get L power that number AB. So now I am defining only L1 AB. Okay, L for Lebesgue, 1 for we are integrating only mod f, not mod f power, and on AB because functions are defined on AB. And this collection, please keep in mind. So now onwards, instead of saying f is Lebesgue integrable, I would say let f belong to L1AB. I am considering this class of functions, L1AB. Something you know about this class by now. For instance, do you see that if f and g are integrable, then f plus g is integrable?
Yes, sir.
That means if f and g are in L1, f plus g is in L1. Similarly, c times f is also in L1. Do you agree? for
Yes,
all
sir.
complex number C or real number C, depending upon whether you are taking your K to be R or C. This K is either R or C, real or complex. So what is that observation tells you about this collection L1AB? Whenever F and G are in L1AB, F plus G is there, alpha F is also there. So what it tells you about L1AB?
L1 is vector space.
It's a vector space. Okay. We shall come back to this vector space later. Now please keep in mind that it is a vector space. I would like to define a metric on it and so on. And these will form the background material for your next course, functional analysis. So wherever certain things are introduced in functional analysis, L1AB or in general, LPAB is going to be concrete examples for the concept that you develop in functional analysis. Okay, and what will be LPAB? You can guess. Collection of all functions. F is measurable and integral A to B mod of power PDM is finite, where P is a real number. Okay, non-negative real number. So that is LPAB. About L1AB and LPAB we will discuss later. Now I just wanted to introduce L1AB notation. That's it. Okay. Now fix F in L1AB. Just means that F is Lebesgue integrable. Okay. And define capital F of X is equal to integral A to X small f of t dm for every x in AB. Like in Riemann integration, you talk about indefinite integral. Here I am defining actually the indefinite integral. But the integral that you see in the right hand side, I mean Lebesgue integral only. That should be clear from the notation dm. I mean the Lebesgue integral. To be precise, I should have written integral over the interval ax. Instead of that, I am writing integral a to x, but that should be clear. Is that okay?
Yes, sir.
Yes,
It is
sir.
Lebesgue integral over the interval a. It is not Riemann integral. Okay. And the right hand side is well defined because you are picking f from
L1AB.
L1AB. So they are all Lebesgue integrable. Okay. Once it is Lebesgue integrable over AB, it will be Lebesgue integrable over AX for any x. That's not hard to see. So it is a well-defined function. Okay. And it is called the indefinite integral, just like in Riemann integration theory. The function f, the function capital F is called the or called an indefinite integral. It is not unique. In fact, you can put a C plus also, or you can vary the lower limit. It may not be from A. It can be from any C between A and B. Okay. So that's why I'm not calling the indefinite integral. Capital F is called an indefinite integral of F. Okay. And what we want to do is to analyze certain things about indefinite integral. That's what the fundamental theorem of calculus does. Okay. And for that, as I told you, I have to collect so much of background material. I will start by introducing or maybe recalling. I don't know whether you have done it as a part of real analysis. The class of functions called functions of bounded variation. Have you heard about functions of bounded variation?
Yes, sir.
Yeah. Yes or no, that doesn't matter. I am going to anyway define it. Okay. Let us introduce or reintroduce the following classes of function. Mainly, I want two classes of function. All these things are towards fundamental theorem of calculus for the Lebesgue integration. First class that I want is bounded variation, functions of bounded variation. And the second classes of functions that I wanted to have is absolute continuous function. You might have heard about continuity and uniform continuity. There is yet another continuity called absolute continuity, and absolute continuity plays a major role in connecting differentiation and integration in the Lebesgue setting. Okay. This is the notion, perhaps it is new to you, absolute continuity, because the main purpose of absolute continuity, main role of absolute continuity comes in Lebesgue theory. So this might have not introduced in the real analysis course. Anyway, so let us define one by one and see certain properties of these functions. I will not be in detail. I will give only the main results. Okay. So a lot of exercises or tutorial problem you will get in when I introduce these two classes. Let f be a function. So let me make that first definition. What do you mean by a function? Bounded variation. Let f be a function defined on a closed bounded interval ab to k, where k can be real or complex. Let us take a partition P. A is equal to x0, x1, x2, so on, xn is equal to b, where x0 less than x1 less than x2 and so on less than xn be a partition of closed bounded interval AB. What I do is you consider each subinterval determined by the partition. A typical subinterval will look like xi minus 1 xi. And on that subinterval, if you look at the variation of f, what is the variation? Variation will be f of xi minus f of xi minus 1. This is the variation of the function in the interval xi minus 1 xi. Do it for each subinterval and sum it. That is summation I is equal to 1 to n modulus of f of xi minus f of xi minus 1. So you look at variation of the function over subinterval, do it for each subinterval and look at their sum. Okay. This quantity I will denote by V for variation over the interval AB. So V subscript A superscript B, P because it depends upon which partition of the function f. So this is the notation. V, A, B, P, F. Okay. Consider this called the variation of f over AB with respect to the partition P. Okay. Now you can change the partition. You can consider different possible partitions of AB. And now you consider, look at supremum of the variation of f with respect to a particular partition and then change the partition. P is a supremum taken over all possible partition. P is a partition of AB. Look at this quantity. Okay. And this quantity is called total variation. First one was variation with respect to a partition. Now it is independent of partition. It depends only on the function and the interval. Is called total variation of f on the interval AB. you can easily see that variation of function over interval with respect to any partition is non-negative. Yes or no?
Yes, sir.
Yes, sir.
And therefore, total variation is also non-negative.
Yes, sir.
But it could be infinity. You are talking about supremum of a non-negative number. It could be infinity because I don't know whether the elements in that set is bounded. Whether that set is bounded or not, I don't know. So supremum could be infinity. If it is finite, we call the function is of bounded variation. Okay. Note that total variation, and that also has a notation which I forgot to mention. Total variation denoted by, this is the notation, denoted by VABF. Now there is no partition coming into picture. You have already taken supremum over all partition. Okay. Could be plus infinity. If it so happens that total variation is finite, then we say that F is of bounded variation. Variation is finite. Total variation is finite. Collection of all variation over different partition is a bounded set. So in many ways you can consider this is called a function of bounded variation. So first we define variation over a partition by looking at variation over each subinterval and summing it. Now take different partition and look at the supremum. Supremum is non-negative, but it could be infinity. In case it is finite, we declare that the function is of bounded variation. Is that clear?
Yes, sir.
Now I should give you a few examples and some properties of bounded variation function. So let me start with some example. Some trivial example is the following. Suppose your f is monotonically increasing or monotonically decreasing for that matter. Okay. Then what will be this VABPF? There is no modulus there, right? If it is monotonically increasing, modulus of f of xi minus f of xi minus 1 would be same as f of xi minus f of xi minus 1. Yes or no?
Yes, sir.
So what will be the sum? It is like a telescoping thing. Many things will cancel. And what will remain in the summation? F of xn minus f of x naught will remain. Am I right?
Yes,
Yes,
sir.
sir.
That is FB minus FA will remain. So variation of F over AB with respect to any partition independent of the partition is a same number, and that number is FB minus FA. Do you agree?
Yes, sir.
Yes,
So
sir.
what will be the supremum? That what will be the total variation?
Will be the same.
F
Same,
minus F.
and it is finite. So total variation is finite, and therefore it is of
Finite.
Bounded
variation.
bounded variation. So what is the observation? Every monotonically increasing or decreasing function. Increasing or decreasing function f from AB to R is of bounded variation. Okay. Note that I will not write the detail, but I will just mention that variation of the function f over any partition over AB will be equal to FB minus FA. And therefore, the total variation is also FB minus FA. It is independent of the partition, which is finite. You are considering real valued function. So FB minus FA will be a finite real number. Okay. For F increasing. Similarly for decreasing. Okay. Now, suppose F and G are two functions. Okay. Which are both of bounded variation. I wanted to observe a few things. Suppose before that, let us observe about one function. Suppose F is of bounded variation. F is of bounded variation. So one example I have given, monotonically increasing or decreasing functions are of bounded variation. Now let me give you one way to get non-example. Examples of functions which are not of bounded variation. Suppose F is of bounded variation, then I observe the following. And this will lead to giving many non-examples. Then F is bounded. I will prove that any function of bounded variation is bounded. Okay. Therefore, if you take an unbounded function on an closed interval AB, that will not be of bounded variation. So you got examples, non-examples of bounded variation function. Is that clear?
Yes,
Yes,
sir.
sir.
So now I have to prove that a bounded variation function will be of bounded, That's easy. So let me just quickly write it. Let f be a function from AB to R be of bounded variation. I have to prove that it is bounded. What is the meaning of bounded variation? The variation is finite. That is, the variation is finite. Okay. Now you consider the interval AB and let X be a point in the closed interval AB. Could be A, could be B, or could be any intermediate point between A and B. Note that modulus of f of x is equal to or less than or equal to, after applying triangle inequality, fx minus fa plus mod fa. Okay. Somehow I want to relate it with the variation. Okay. So take this as a partition A, X, B. Now you have a partition of AB. Look at the partition P equal to, give me 2 minutes, A, X, B. This is the partition I am interested in. Then modulus of fx, you have seen that it is less than or equal to modulus of fx minus fa plus modulus of fa, which will be less than or equal to modulus of fx minus fa plus modulus of fb minus fx, because modulus of fb minus fx will be non-negative and I am adding a non-negative quantity, plus mod fa. I hope you agree.
Yes, sir.
I introduced a new non-negative term. Now you look at first and second term and their sum. What is it actually? Fx minus fa modulus plus fb minus fx modulus. What is it? It's variation, right? It's variation of function f over the partition P that I have taken. Do you agree?
Yes, sir.
Yes, sir.
Plus mod
Yes,
fa.
sir.
Plus mod fa. Okay. But variation over a particular partition is less than or equal to total variation. Agree? Because total variation is supremum.
Yes, sir.
But you know that the total variation is finite. It's a finite number. Okay. So you call this whatever is appearing in the right hand side as m. Define it to be m. Okay. Then you will get mod fx is less than or equal to m for all x. Means
Fx is bounded.
f is bounded. F is bounded. Okay. Since somebody told fx is bounded, again let me tell you that I always want to distinguish between function and function value. Many times we don't bother. F and fx we will use synonymously. But I would say that f is function and fx is value of the function at a particular point x. So fx will be always a real number. So there is no meaning in talking about fx is bounded. I would rather say f is bounded. Sin x is not a function. Sin is function. You understand the difference?
Yes, sir.
But many a times we don't bother. We will call sin x is a function. But it is better to make that distinction. Okay, function and function value. Anyway, so every bounded variation function is of bounded. Therefore, if you take an unbounded function, it will give you a non-example of bounded variation function. Now I will stop with the following exercise. You can prove that if f comma g from AB to R or AB to K are of bounded variation, please try. Are of bounded variation. I will not supply the details in the next lecture for the same comment. Are of bounded variation, then f plus g, cf, fg are all of bounded variation, where c is a scalar for any C in K, where K is real or complex. So basically it tells you that collection of all bounded variation function is well behaved. It's a good class. Okay. And the first two will tell you that the collection of all bounded variation function on AB is
Vector
Vector
space.
space.
a vector space. Okay. That is collection of all functions of bounded variation. I will stop with this. On AB is well behaved with respect to plus, with respect to scalar multiplication, with respect to product, and so on. In particular, it is a vector space. And that has a standard notation BVAB. Is collection of all f from AB to R or AB to C, where f is of bounded variation. Total variation is finite. Okay. So I would stop with this, but keep in mind what is our next agenda. The next agenda is to prove fundamental theorem of calculus in the Lebesgue setting. We are just collecting materials for it. We started with the bounded variation and we observe a few things about bounded variation. We shall observe a few more facts about bounded variation function, and then we go to next class, absolute continuity function. Then we explore certain connection between these two classes, absolute continuity and the bounded variation. Then we have to go back to DCT and so on, some consequence of DCT. With all this background material, finally I will state and prove fundamental theorem of calculus for the Lebesgue setting. Okay. I think by next lecture I can finish FTC. Yeah, let me stop with that. Thank you.